smooth introduction and for the invitation. Yeah, I'm honored. So today I'm going to do something unusual for me. Most of you, I think, are familiar with what I usually talk about. So usually I do things in dimension 4, and often it's algebraic and analytic as well as geometric. But today I will try to do something in dimension 3, mostly in some combinatorial way. So as an effort to suit you better, so suit the majority of you. So, all right, so let me start with a definition which measures how complicated a three-manifold is. So, let me start with the simplicial version. So, the simplicial complexity which I denote by C, simplicial of a three-manifold M. Here in this talk, M is always a three-manifold. This is the minimum of the number of tetrahedra in a triangulation. Of course, of M. So if you need more tetrahedra to triangulate your three-manifold, then it's more complicated, and it's reflected exactly by this definition. So a triangulation here is just a simplicial complex structure. All right. It's natural to think about.
So ideal
no, this is M is always closed in this talk. All right, so everything's compact, and the triangulation is just a standard simplicial complex structure as in the elementary algebraic topology. So, well, in the literature, there is a similar version of complexity defined in terms of some relaxed version of triangulation. So which is often called the pseudo-simplicial triangulation. So it's defined to be a collection of tetrahedra together with identifications, affine identifications, of faces. In other words, the two simplices in the boundary, such that because we have the identification, we can think of the quotient space. So as you expect, we want to build them as a quotient space. So this is more flexible in the sense that, for instance, here we are allowed to identify two different vertices of a single tetrahedron. But in a simplicial complex, it's not allowed. So essentially the same idea, but slightly different. So it's easy to see that so let's define a pseudo-simplicial version of the complexity. So this is minimum number of tetrahedra in a pseudo-simplicial triangulation. Then it's easy to see that and here is some comment about the name. So I'm going to call this simplicial complexity, and then it would be natural to call this a pseudo-simplicial complexity, but let me just call this complexity of M, because this name is used in the literature. All right? So the complexity is bounded above by simplicial complexity, right? Because a simplicial complex gives us a pseudo-simplicial triangulation. And we also have another inequality. So if you have this relaxed version of triangulation, then you can just subdivide it to make it correct simplicial complex. So it turns out that if you take the second barycentric subdivision, then you will get a simplicial complex structure. The problem is resolved, so it's enough to count the number of tetrahedra in the second barycentric subdivision. It's easy combinatorial exercise. So whenever you perform a barycentric subdivision once, you have this factor, and you do it twice. So you have this, and then this. All right? So up to constant factors, they are equivalent essentially. All right? Yes?
For surface case, what is the answer?
Surface is two-dimensional, so this should be 3, I think.
It's determined by genus, the formula.
This constant you are asking about, no?
Just the number, the indicate triangulation, right?
Yeah, so I'm talking about 3 manifolds. I'm looking at tetrahedra, but if you are interested in surfaces, then it's natural to look at triangles.
So you know the answer for?
Answer for what?
In terms of genus, maybe.
In terms of the genus. Yeah, it should be known. I can just give an estimate, but it should be known. Yeah, that's easy.
It's much easier, right?
Yeah, much easier, yeah. Right. That's why usually we think of dimension 3 and higher. Dimension 2 is a lot easier. So asymptotically, those two notions are equivalent. So, but here are some other similar flavor ideas. So why do we think of simplicial complexity? Because it's natural to represent a 3-manifold as a triangulation. So that's most combinatorial method, but there are other ways, other standard ways to represent a 3-manifold. All right, so for instance, we can think of a surgery description, in other words, a framed link. So this gives us another similar definition. So let me denote it by surgery complexity of M. Right? So this is the minimum taken over framed links such that if you perform surgery, then you get M. All right? So it's a diagram like this, for instance, 0, 1, you will get certain 3-manifold. All right? So I'm going to think of integral coefficients only. Namely, I don't use rational coefficients. All right? Then the first thing we think of naturally is how complicated this link is. So I said that I want to be combinatorial. So the most natural, one of the most natural measure for the complication of a link is its crossing number. Just to look at diagram, take the minimal number of crossings of a diagram for the given link. So for some reason, I need to multiply by 2. But that's...
So do you forget the integers in the components?
I will consider it. All right? So you see some space there. So that's for you. All right? Yeah, of course, I need to think of the framing, because if I forget the framing, then I lose too much information. Lens spaces, for instance, right? So let me define something regarding the framing. So it's simple again. Let's take the sum of the framings of the components. All right?
Not
To put the absolute value.
Oh, yes. So, all right. Good point. And I need a little bit more actually. Suppose, for instance, this thing. What is this? This is S1 cross S2, but this is not reflected here. Crossing number 0 and framing contribution 0. So, but I don't want to ignore this. So let's add something, which I denote by N over L. This is the number of split zero framed unmarried component, namely something like this. All right? So I'm just counting, in other words, factors of connected sum ends of S1 cross S2, which is easily identified from the diagram. Okay? So this is my definition of surgery complexity. And because I'm talking about basic fundamental methods to represent three manifold, there is one more at least, I think, which was discussed in other talks in this workshop. You used in your talk, for instance, to describe a three manifold Giga diagram, right? So Giga decomposition can also be considered. So this gives us, leads us to the following notion of complexity naturally. So let's see. So I'm going to again take a minimum of the Giga splitting information over all possible Giga splittings. So in order to describe a Giga splitting, let me just take a mapping class on a genus G surface where G is arbitrary. All right? All right, then I want to measure now how this mapping class, how much complicated this mapping class is. So now I adapt some fundamental idea from geometric group theory. So this is a group, mapping class group, and a natural thing to measure the complication of an element in a group is to look at the word length. All right, so I'm going to take the word length, but in order to talk about word length explicitly, I need to take a set of generators. So in case of mapping class group, there are several standard generating sets known classically, but I'm going to take the simplest one. So Ricorici proved that, for instance, in this genus 3 case, plus minus 1 then twist along those curves form a generating set for the mapping class group. In general, for genus G, it's enough to think of the generalization of this picture, which consists of 3G minus 1 curves, because I don't have one guy here, right? So 3, for each wall I have 3, but 2 for the last thing. So those are called the Ricorici twists. And then let me call the word length with respect to this choice of generating set the Ricorici word length of a mapping class. So I'm taking the minimum over all of the possibilities. All right?
genus means you consider surfaces of different genus.
Right, right. Any genus is fine. Actually, it may be possible to reduce this value by increasing the genus.
Okay.
Yeah, it's possible. I don't have a concrete example for you right now, but
Okay.
yeah, we allow it. Yeah. All right. So definitions are easy to formulate, but computing them is extremely hard. For instance, that's a common thing about combinatorially defined invariants. It's easy to define, natural to consider, but hard to compute and determine. The determination problem for instance, this version of complexity was studied extensively in the literature, but the precise value is known only for very limited class of three manifolds. So it's a very interesting problem. So finding, because of the definition using the minimum, it's relatively easier to find an upper bound. For instance, if you have a triangulation, then that's going to give a particular upper bound for the simplicial or just complexity. If you have any Higa splitting in terms of a mapping class, then you will get an upper bound for the Higa licorice complexity. Right? But finding a lower bound is difficult. So let's talk about some easier parts. Okay? So the first thing I'm going to describe is sort of some relationships between the complexities. Let's call it Theorem A. If my three manifold is not the three sphere, then the simplicial complexity is bounded by 692 times the Higard licorice complexity. Okay, that's my first theorem. So why do I exclude S3? Because if it's S3, then my Higa diagram is empty, right? So the minimum is 0. So, but this is non-zero. I have at least one tetrahedron to form any non-empty three manifold. So this kind of inequality won't hold for S3, but except this obvious case, we have that inequality. Right? So given this statement, how do you try to prove this? Given a all right, let's think of the following version first. Surgery complexity case is easier to describe. So let me change my theorem A, and the previous statement will going to be my theorem B, right? So how would I prove this? Given a surgery description, I'm going to construct a triangulation. Right? Then that will going to give us a sort of this type of inequality, upper bound for the simplicial complexity. So in other words, I'm doing just a purely combinatorial thing, as I claimed at the beginning. So I'm good, at least so far, I think. So let me just describe some combinatorial ideas. All right, so I like to draw pictures, so let me do that. So let's think of, for instance, this knot. Okay, so some framing, let's say D. This is now a three manifold. So, and I'm going to tell you the idea how to triangulate this three manifold. So let's draw the dual graph. All right, I'm doing really combinatorial thing. So what's the dual graph? So for each face, we have a vertex, and for each edge, we have a crossing edge, right? So we have something like this, right? Okay, and let's regard this as a top view of our knot in S3, and let's cut S3 along a cylinder with base this foreground rectangle. Then the picture is going to be something like this. I'm going to this kind of stream. Now the top is here, and then this one is going to be a tube, empty tube like this, all right? And this guy is below this guy, so I have another empty tube like this, right? And if I redraw this top view, then I see this one and this one with crossing here, right? Are you with me? So let's cut this further. How? Just use your knife and use it vertically to cut this along the vertical plane containing this line and that line. Then I will get 4 pieces. Okay? So the back piece is going to be again like this, a little bit narrower, but we are topologists so that we can scale whatever we want. But this thing, this hole is cut again. So this one is going to be shown like this. Are you with me? All right. And this one, the back part, back half of this tube is going to be shown here. Not this way, right? Okay. So I got a tube with some preferred simplicial complex structure. All right. So this is actually a cube, right? Okay. So I can just triangulate this two-dimensional picture by adding edges like this, right? Okay, and there is a hidden vertex here, and this cube is indeed a cone of this face part, front part, taken at this cone point, right? So just take a cone of this two-dimensional triangulation to get a three-dimensional triangulation, and just glue them to rebuild the exterior of my link. Actually, I get a triangulation in this way. All right? But I want to get a surgery manifold. But if the framing is the blackboard framing, then it's not difficult to fill in these empty tubes with a nicely triangulated solid torus, if it's blackboard framing. So actually, by just filling in this thing with tori, I get a triangulation of my manifold, given as this surgery description. And I guess it's pretty convincing that the resulting number of tetrahedra is linear. Because for each crossing, I have one guy like this and 4 guys like this. And we have exactly 2 guys like this in each piece. So it's going to be increased. The number of tetrahedra is increasing linearly in terms of with respect to the number of crossings. So that's how I get this kind of linear inequality. So it's fun to do this kind of combinatorial geometry.
Is the number 96 the best possible we can get?
That's a good question. Of course not, I think. 95 must work, I guess. So that's a very good question. All right? So I will address that issue a little bit more in a minute. Thank you for asking. Okay. So, all right. So the theorem B, which was stated before, is indeed similar. Now the coefficient is bigger, but we have the same kind of inequality. It's convincing because Higgs diagrams are more efficient in describing A3 manifold. So given this, how do you try to prove this? If you read Ralphson's carefully, for instance, then you learned how to produce a surgery diagram, surgery description from a Higgs splitting. The idea is this. Actually, it's Licorice's idea, but I guess most of you learned this from Ralphson. Yeah, I do know that remembering it is different from that you learned, but so let me remind it quickly. So, for instance, suppose I do dent twist along this guy. Then the effect is the same as doing surgery on such a curve. And suppose I do another dent twist on this guy. Then I add exactly the same shape of component, but now I'm going to shift it, push it a little bit to get this. And suppose I do a dent twist along this guy, then I need another component for the surgery description. So in this way, we could try to translate this word expression of a mapping class to such a surgery picture and invoke theorem A. Well, when I realized this, I was happy because the nature of a mathematician is to reduce a given new problem to the older problems. But after that, I realized that this is not satisfactory. For instance, suppose, let's call this 1, this 2, this 3, and let's think of dent twist along curve 1, curve 2, curve 3, and then again curve 1, curve 2, curve 3. Then what you would get is a link like this. Okay, so here the length is increasing linearly, but now I have quadratic increase of the number of crossings. So this method won't give us such a linear inequality. So we need to be a little bit more clever. So let me just mention briefly what the idea here is. Here the idea was to look at the planar diagram, right? It's a diagram on a plane, but now such a link can be viewed as a link in, if this is my surface sigma g, then this can be viewed as a link in sigma g cross interval. Okay? And we can invoke the same idea as the planar case to triangulate this thing, exterior of this link inside this thing, and then promote it to a triangulation of S3. Using this method, roughly speaking, this inequality is proven. Right? So we need a little bit more idea, but this is still not very much complicated. Right? So I'm going to return to Taehi's question. Are they best possible? Of course, no. The answer must be no. Right? I don't have a explicit proof that, for instance, 690 would work, but I can bet my money? Yes, I can. So the questions now, what's the most efficient way to give such a bound? But here is something interesting. I'm going to tell you that this is actually optimal in some sense. More precisely, this is asymptotically the best. For example, I cannot replace this side as a square root function. For any large constant, for instance, this inequality is not true for any large constant. So to state it formally, let me define the following function formally. Let's define such a function, SHL of L. What does that mean? I look at the manifolds whose Hegel licorice complexity is n most L. And I look at the simplicial complexity of that guy and take the supremum. All right, so this is therefore the sort of largest possible value of this guy with respect to this guy. All right? Then this function is obviously in the class of big O of L. What does that mean? This function is bounded by a constant times L linear function for all large L. So we say that f of L lies in O of G. Let's use n for general. If and only if f of n is bounded by some constant times g of n for all large n, standard complexity notation. And this is the same as that the rim sup of fn over gn is finite. All right? So this is kind of inequality that the worst case simplicial complexity is n most L asymptotically. So that's true because we have this inequality, right? So the actual content is the following. Let me define, can you read this part? Yeah, so here is another similar notion. We say that Fn is in small o of Gn if the rim sup of F over G is 0. So Gn is stronger asymptotically, strictly greater. Okay? And Fn is in omega of Gn if Fn is not in small o of Gn. In other words, Fn is not strictly smaller than G. By definition, this is none more than that the rim sup of F over G is strictly positive. All right? So this is the notion of this, and this is the notion of this, right? And this is the notion of this, all right? So we have one inequality, so we wonder whether this complexity function can be strictly smaller than linear function. My answer is no. It's not possible. In other words, this function also lies in the class of big omega.
this does not depend on m. For any m, we have this freedom.
In this definition,
I mean the theorem. I mean, but
theorem. If this theorem is not about a particular m, right? So function is defined by considering all possible three manifolds.
So soup means soup for all m. Okay.
So for all m satisfying this, you're right. Precise. Exactly. Okay. In fact, so looking at this is actually considering the lim sup of the worst case simplicial complexity with respect to the Higard-Licorice complexity over the given complexity L, and we know that this is bounded by this, and I do know that this is greater than or equal to 1. So the supremum is explicitly estimated in this way. So it's in particular positive and bounded above. So a question might be asked, for instance, can we give some better combinatorial method to give a triangulation in order to make this closer to 1? Or can we improve 1 to make it closer to the upper bound? Right? I think this is an interesting combinatorial question. So proving this lower bound actually is harder than the combinatorial techniques I described. We need to actually, in order to do this, we need to find some lower bound for the simplicial complexity. Yes, question?
So you have some infinite sequence of manifolds.
Exactly.
You need some technique to bound.
Yeah, exactly. So actually, the range space Ln1 can be used exactly in the same way as you expected.
Okay.
So
Okay.
it's a simplification, but can it prove like the project theorem A with opposite way, like bound C sim of M?
Yeah, that's right. So yeah. That's the question I want to ask. So
I mean, here you didn't fix M. But theorem A is for any M, but there, I mean, this is a
right. So the question might be formulated in this way. Is there some constant, because C is used everywhere, let's use D, all right? Such that C surgery M, or similarly for Higard, Licorice, whatever it is bounded by D times the simplicial complexity. If we had this, then we would conclude that the Higard-Licorice complexity has exactly the same asymptotic growth as the simplicial complexity, but I don't know. So this is another question, interesting question, which can be, I guess, addressed purely combinatorially. Right? So CHL or C surgery in both cases. All right, so I don't know, we don't have that much time, but let me just try to tell you about just one more thing. So here is a stable version of the complexity, which is again natural from the viewpoint of recent three-manifold topology. So this is defined by Milnor and Thurston. According to MathSciNet, there are exactly only 2 papers joined by Milnor and Thurston. Maybe if you need to name 2 greatest topologists of modern mathematics. And after Poincaré, I guess these two. But this definition is given in one of those two joint papers. So it's going to be denoted by sigma m. This is now the infimum of the complexity of m tilde over something where m tilde is a, let's use k, is a k-fold cover of m. Then it's natural, because we take k-fold cover, it's natural to expect a factor of k for the triangulation. So we divide it by k and take the infimum of all these ratios. So it's kind of looking at the finite covers. All right? So it's related to this. I need to talk about the Gromf norm. This is another really interesting quantity. So to define this, let's do very little bit of algebraic topology. So let's consider the singular chain complex of my manifold with real coefficients. Then the Gromf norm of M is defined to be the infimum taken over chains. So a chain can be now written as a linear combination of singular simplices. So my sigma is a singular simplex. I'm going to look at chains which represent the fundamental class of M. All right? So it's kind of triangulation, but it's sort of homological. We want to express the manifold using now singular simplices with even real coefficients. And then how much complicated is this guy? It's natural to look at the coefficient. So we take the L1 norm, namely just take the sum of absolute values of the real coefficients of the chain, actually a cycle. Then, oops, let me just finish quickly. I don't like that, so how much is it for each minute? Is it for free, Tae-hee? Well, it's easy to actually see that the stable version is not greater than the usual version of complexity. Right? And it's a little bit more non-trivial, but it's not terribly difficult to see that the Gromf norm is also bounded by this stable complexity. So there is more known. There is a constant such that this guy, stable complexity, is bounded by a constant times the Gromf norm for hyperbolic manifolds. Gromf norm is meaningful mostly for hyperbolic manifolds because it's known to be the volume, hyperbolic volume, divided by a constant V3, which is defined to be the volume of a regular ideal tetrahedron in H3, the hyperbolic space, for hyperbolic manifolds. And if it's not hyperbolic, then this is actually the sum of, Gromf norm is the sum of the volumes of the hyperbolic pieces in the JSJ decomposition. So in particular for a graph manifold, when the pieces are all Seifert-Fibert, non-hyperbolic, the volume is 0 and it gives us no information. So the hyperbolic case is most interesting. And in that case, we have a constant times Gromf norm bound for the stable complexity. So they are kind of the same kind of quantity asymptotically. So the questions whether the gap between the Graph norm or the stable complexity and the usual complexity can be large. All right, so my final statement is the following. Here is a two-bridge knot. We know what a two-bridge knot is from this conference, right? And there are two end crossings. And let's do D-framed surgery. All right? This system, D is fixed. All right? Then the theorem is that if n is greater than 2, then Mn is hyperbolic. And Cmn minus the gap between those two constant complexities is bounded by the following very interesting number. Well, this is why I need my note. I can't remember the number. So the important thing is that because D is a constant, this is a linear term, so this goes to infinity. Sn goes to infinity. So I have a family, explicit family of hyperbolic manifolds for which this gap can be arbitrarily large. So in this way, I would say that there are a lot of interesting questions about those combinatorially defined notions of complexities of three manifolds, which can be pretty often addressed purely combinatorially or by employing some other nice technologies. This theorem is such an example, but I would like to draw some attention about these kind of notions and questions. Let me stop here. Sorry for taking more time. Thank you.